All right, hello. Today we are going to be finishing up the notes for modern atomic theory. I'm going to review real quick the other stuff that we talked about before, and then we'll get into the actual new stuff. So we talked about, in the last video, atoms made up of two regions. The nucleus, which is the very tiny dot in the center, and the electron cloud, which is everything else. Mostly empty space, relatively large compared to the atom. Okay, so the nucleus is small, dense, and positively charged. The electron cloud is relatively large, has a very low density, and is negatively charged. The electron cloud is 99% of the volume of the atom, and the nucleus is 99% of the mass. Okay, and then those two regions are filled with particles. The three subatomic particles that we talked about are protons, neutrons, and electrons. Protons are positive, neutrons are neutral, and both of those are in the nucleus. Electrons are negative and significantly smaller, and those are found in the electron cloud. They also move a lot faster. One other thing that we mentioned, and this is going to kind of tie in with everything we're talking about today, the actual significance and purpose of each of those particles. Something just fell over. The actual function for each of those particles, the number of protons identifies the element, because it's unique for each element. The number of neutrons stabilizes the nucleus because it keeps the protons away from each other. And the electrons are what actually form bonds, because while they're sprinting around in their massive little circles, moving at 1,000,000 billion miles an hour, they are also capable of actually leaving the atom, and because of that they can form bonds with other atoms. So electrons leaving forms bonds. Now, we mentioned that the number of protons dictates the atom. I think I spent a pretty significant amount of time talking about that in the last video. But I didn't spend much time talking about these two other terms that have to do with an atom. So there's three terms that can be used to describe every atom. Its element, its isotope, and its ion. All three of those, every atom has an identity of one of those three things. The number of protons dictates what element it is. The number of neutrons, in addition to stabilizing the nucleus, it dictates what isotope that atom is. And the number of electrons dictates what the ion is. So every atom has an ionic charge. It may be 0, but it has an ionic charge. That's its ion identity. I almost just held up my middle finger. Also has an isotope identity, which is usually a number. It is not the number of neutrons. We'll come back to that. And then obviously the third one we've already talked about, that is the element's actual name. I'm going to pause this because I'm about to die in this hoodie, so give me a second. And I'm back. Okay. So the main thing we're going to talk about today is ions and isotopes, because we already talked about elements. Okay, I guess I will mention one little bit. First off, in the notes, there has been a change since you printed them, and I apologize for that, but I realized I meant to change them before, and so I changed them just last week on Friday. So, now at the top of the second page, I have changed a couple things. I have added a couple of things. So you might want to go in and actually pull up the digital copy of the notes and decide if you want to reprint those or not. But those are the notes that I'm going to be referencing. Okay, so first off, for elements, there are 118 of them, and that is dictated by the number of protons. There are actually more than 118. There are just only 118 that are on the periodic table as it is currently put together. I believe they've actually discovered through element 123 at this point. That might be a little outdated. It might be more like 125, 127, somewhere in there. But There are only 118 on the periodic table so far. Each one of those, what makes them different is the number of protons. We talked about that last week. If it has 74 protons, tungsten. If it has 1, hydrogen. 3, lithium. That's the identity of the element. What we didn't talk about is every element has multiple possible isotopes, and some have multiple possible ions. Actually, all of them have multiple possible ions. There's just some only have 2. But we're not going to worry too much about that in this class. So, let's start with isotopes, because I think this one is a little easier to wrap your head around. When we talk about isotopes, what we're talking about is the different number of neutrons that are in that atom. For example, there are 3 isotopes of hydrogen, or at least 3 relatively common ones. Those are hydrogen, oh so creatively named, deuterium, and tritium. Okay, hydrogen has no neutrons. It's the only atom, the only isotope in existence that has no neutrons. Every other atom and every isotope of every atom has at least 1 neutron. In fact, most of them have at least 2. But hydrogen, standard hydrogen, has no neutrons. Okay, so I'm going to show you something here called isotope notation, which we're going to spend a little bit more time talking about in the next section of notes, basic atomic calculations. And I've also just realized that I haven't turned on my overhead light, so I'm going to pause this again and go do that. One of these days I'll figure out what I'm doing. Alright, so hydrogen, deuterium, and tritium. You do not have to know these words. I am just using them as an example. Okay, hydrogen has 0 neutrons, deuterium has 1, and tritium has 2. All 3 of these have only 1 proton. Okay, now, back in the day, it was common for every isotope to have its own custom name, which is why these 3 elements, or these 3 isotopes, all have their own different name. But as we discovered more and more elements, it became clear that that was not going to be an effective way to identify isotopes, because there's way too many of them. So we came up with a standardized way of identifying isotopes instead. Okay, so hydrogen with no neutrons, its standard isotope notation would be hydrogen 1. Okay, where this 1 is something called the mass number. The mass number is something else we haven't talked about yet, so I'm going to write that down here. The mass number, which is abbreviated MN, because I'm creative like that, is equal to the number of protons plus the number of neutrons. Okay, so deuterium is hydrogen, but it's an isotope of hydrogen that has 1 neutron. So the isotope notation, instead of being hydrogen 1, is hydrogen 2. Because this is the mass number. Deuterium is still hydrogen, so it has 1 proton, but it also has 1 neutron. So mass number of 2, 1 proton, 1 neutron. So tritium then, which has 2 neutrons, in today's nomenclature would be hydrogen 3. Okay, so these are modern day isotope notations. We don't really, in hydrogen's case, we use some of these, like deuterium is actually pretty common. You may have heard of it if you're a nerd. Tritium is less common, but if you're a Star Trek fan, you may have heard of tritium. But for the most part, most people aren't familiar with these. You see these most of the time. Okay, so for example, here's an example of an isotope, or 2, I'm going to give you 3 isotopes of a different element. Carbon. So carbon 12, carbon 13, and carbon 14. Okay, these are different isotopes of carbon. Now, you might have noticed that I abbreviated the carbon this time, whereas here I wrote out hydrogen. Okay, that's because these 3 are what's called longhand isotope notation, while these three down here are what's called shorthand isotope notation. The difference is just the beginning part here. Longhand, we use the whole name. In shorthand, we use just the symbol. The numbers are still the mass numbers. So in carbon-12, the mass number is 12. Well, how many neutrons does it have then? That's the question we usually want to know, is how many neutrons. Okay, well, if it's carbon, how many protons does it have? Well, it has to have 6. So the number of neutrons in carbon-12 is also 6, because 6 plus 6 gives us 12. 6 protons, 6 neutrons gives us a mass number of 12. So carbon-13 then is going to have 7, and carbon-14, which you've actually probably heard of, is going to have 8 neutrons. Wow, that almost looks like an 8. That's there. Now it looks like an 8. Okay, so that's going to have 8 neutrons. So the difference in isotopes is how many neutrons it has. Okay, so we identify that isotope by stating the mass number. That means the mass number is intrinsically linked to the number of neutrons. When you see the word or term or phrase or abbreviation for mass number, in your head you need to go, okay, that has to do with neutrons. That needs to be a connection you're making in your head. Neutrons, mass number. Element, protons. Okay, those are how those relationships work. Which means it shouldn't come as a huge surprise to you that the ion, or ionic charge, as we call it, is tied to the number of electrons. So, for example, if we had carbide, or carbon with a -4 here, okay, this is the charge. The ionic charge is always written as an exponent, and you're going to see that a lot in several different notations as we go through this unit. But this is going to be the ionic charge, okay, or the ion. This is the identity of the ion. It's a -4. Okay, well, how many electrons does it have? Because that's what we want to get from the ion. If it's got a charge of -4, the ionic charge is equal to the number of protons minus the number of electrons. So if it's negative, this number is bigger. If it's positive, this number is bigger. Okay, so we have -4. We know 100% there has to be 6 protons, because carbon means 6 protons. We just talked about that here. So if it has a charge of -4, then the number of electrons has to be 4 more than 6, or 10. There has to be 10 electrons. What about sulfur -2? Well, if there's a -2 charge on sulfur, then sulfur has, oh boy, 16 protons. So if it has a charge of -2, I've got to check that now and make sure I'm saying that right. Does sulfur have yeah, 16. I was right. Okay. So if it's got a charge of -2, that means it has 2 more electrons than protons. So therefore, it must have 18 electrons. Then we have aluminum. Aluminum +3. Well, if it's a positive charge, that means the number of protons is bigger. So +3 means that we have 3 more protons. Okay, well, aluminum, there's an L in aluminum, by the way. Aluminum has to have 13 protons to be aluminum. So that means we've got 3 extra protons. There are 3 protons total, so there's 10 electrons. That is this in a nutshell. We are going to do way more with this when we start talking about basic atomic calculations tomorrow. Okay, or I guess I should say in the next video. But that's it in a nutshell. Okay, isotope is determined based on the number of neutrons, but we report the mass number not the number of neutrons directly. And then the ionic charge comes from the number of electrons. But again, we report the charge most of the time, not the number of electrons directly, because you can figure out the number of electrons. And most of the time, when it comes to electrons and neutrons, we don't really care how many electrons or neutrons there are, because that doesn't affect how the atom's going to behave. What we really need to know is not the electrons, but the ionic charge. What we really need to know is not the neutrons, but the mass number. So we're going to be doing a lot of stuff going back and forth between those calculations, because I want you to be able to, without having to think about it, convert mass number to neutrons, or more importantly, convert neutrons to mass number. Likewise, electrons in ionic charge. You need to be able to go back and forth between those without having to stop and think about it. Okay? Now, none of the stuff that we talked about today, except for in that very first review, which was 2, 3, maybe 4 minutes, is going to be on the quiz over modern atomic theory. This is all more prep stuff, introduction stuff for basic atomic calculations, which we're going to do next. So, review the quiz, go back to that practice quiz, because that's probably the next most important thing for you to work on. With that said, that's all for this video. Have a wonderful day, night, evening, afternoon, whatever, and I'll see y'all next time.